Good afternoon, everyone. My name is David Domingo, and I'll be presenting Kamino, efficient VM allocation at scale with latency-driven, cache-aware scheduling. This is a joint work with Microsoft Research, Microsoft Azure, and Rutgers University. So let's get started. Today, cloud providers such as Microsoft Azure provide instant online access to computing resources. To do this, cloud providers operate data centers around the world filled with readily available hardware and allow customers to rent computing resources via virtual machines, referred to as VMs for short. The cloud providers allocate these VMs on physical machines and then allow customers to access them over the internet. With VMs, customers can pay for what they need when they need it, allowing customers to save on infrastructure capital costs and flexibly scale according to their needs. Now, one of the main challenges for cloud providers is to figure out where to place VMs over potentially hundreds of thousands of machines. Cloud providers need to handle a large variety of VM configurations that customers can request. VMs can be configured with varying amounts of hardware and be configured with preferences such as location. For example, typical classes of VMs have configurations targeted towards particular types of computation, such as memory-intensive, storage-intensive, and GPU-intensive workloads. Additionally, VM allocation must also consider platform efficiency goals to maximize hardware utilization and minimize resource waste through approaches such as machine packing. Because of this, the process of actually resolving a VM request can be computationally expensive, often involving complex set manipulations and comparisons to filter and sort available inventory. For example, to resolve a VM request, some cloud providers carry the following process. When a VMware comes in, available clusters are filtered down to those that have machines that satisfy the VM request constraints. The resulting set of clusters is then sorted based on request preferences as well as deployment preferences of the cloud provider. Next, one of the top clusters is selected, and the same process is repeated for the machines in the cluster. The machines are filtered down based on constraints and then sorted based on preferences. Finally, one of the top machines is selected for the VM to be placed on. In practice, cloud providers must scale this intensive process to accommodate customer demand and the growing infrastructure to match. They must be able to support high VM request throughput to handle the many VM requests that may come in at any given moment, and support low VM request latencies to enable customers to deploy and scale fast. Over the years, there have been several systems such as Google's Omega, Microsoft's Protean, Meta's Twine, and VMware's DRS that have demonstrated practical approaches to effectively manage allocations across thousands of machines across multiple clusters. Additionally, there have been ongoing efforts to maintain operational efficiency and service quality at scale using approaches such as VM lifetime predictions and scalable admission control. In this particular work, we'll be focusing on managing VM request latencies for Protean, Microsoft's VM allocator. Protean is Microsoft Azure's VM allocator, and it scales VM allocation with the following main approaches. First, instead of using one main allocator to resolve requests, it uses multiple allocators, which it calls allocator agents, to process VM requests in parallel. With this, incoming requests are placed on a global queue where it can be pulled by free allocator agents, effectively load balancing requests. Protean can further scale by using multiple machines or nodes to employ additional allocator agents. Most importantly, to improve request latency, Protean allows allocator agents to use available memory as request evaluation caches, caching feasible machine sets for particular request types. These cache sets are then used to avoid recomputation for future similar requests. With these approaches, Protean is able to achieve high request throughput and low latencies on the order of tens of milliseconds. However, although Protean in practice is able to achieve high VM request throughput, we still see instances of high request latencies. Here we plot the request latencies throughout the day for a high traffic node. On the x-axis, we have the time of day, and on the y-axis, we have the latency. Each dot represents a single VM request. We see that throughout the day, there are bursts of requests due to batch deployments, auto-scaling, and capacity reservations. And unfortunately, around these bursts, average and tail latencies significantly suffer. This is not ideal, as we want to ensure consistent deployment and scaling speeds for customers. So how can we improve these latencies under these bursts? One common approach to improve latency is to increase parallelism. By having more allocator agents, more VM requests can be processed in parallel, potentially minimizing wait times and latencies. To see if this could work, we simulate Protean's performance with increasing allocator agent counts within a node. On the x-axis, we have the allocator agent count, and on the y-axis, we have the average latency normalized to the default node configuration of 4 allocator agents. The lower, the better. Additionally, we break down the latencies into their wait and processing time components. First, we observe that as allocator agent counts increase, wait times decrease. However, as allocator agent counts increase, processing times also increase, resulting in limited latency improvements. So the question now is, why do these processing times increase? What we found is that this is because of memory bottlenecks. We sampled the resource usage from 4 popular allocator nodes, and we found high memory usage around 90%. This suggests allocator agents are tightly constrained by memory. What this means is that attempts to scale allocator agent counts increases potential cache duplication, which in turn reduces memory efficiency and the ability for individual allocator agents to cache popular request types. What this results in are higher cache misses, forcing expensive recomputation, leading to increased processing times. We can perhaps add more allocator nodes to completely eliminate wait times, as well as increase memory capacity to maintain cache performance, but this would lead to potential resource waste. So can we do better? Can we achieve lower latencies by improving memory efficiency instead? To improve memory efficiency, we can try and maximize cache locality. To do this, we can send the same request types to the same allocator agents. However, differences in request type popularity may cause load imbalance, so we need some sort of load balancing to ensure minimal delays. Unfortunately, maximizing cache reuse together with load balancing actually doesn't do so well. To demonstrate this, we induce cache locality using by hashing requests, similar to consistent hashing used to load balance across servers, and use work stealing to allow idle allocator agents to steal requests from busy ones, effectively handling potential load imbalance. Here we plot the improvements for average and 90th percentile tail latencies. On the x-axis, we have the latency metric, and on the y-axis, we have the improvement in percents. The higher, the better. Overall, we see minimal improvements of only 4% and 9% for average and tail latencies, respectively. What's interesting is, though, that the top whiskers show that some latencies can be significantly improved because of increased cache reuse and cache locality. However, on the other hand, the quartile boxes show that for some latencies, the improvements for latencies are minimal or even negative because of load balancing, causing cache misses and excessive cache duplication. In the end, these results show that cache reuse and load balancing are at odds. Although both approaches try and reduce latencies in their own way, they ultimately end up working against each other. So the question is, what causes this? What makes cache reuse with load balancing challenging? And the reason is high request latency variability. We depict this trend by sampling the hit and miss times of 400 popular request types. Each point represents a single request type. On the x-axis, we have the request type's hit latency, and on the y-axis, we have the request type's miss latency. We can see how the latencies across request types can highly vary due to differences in constraints and required computation. And in some cases, the hit times of particular request types can be larger than the miss times of others. Take, for example, the request enclosed by these boxes. The request types enclosed within the red box are those whose latencies are more than 500 milliseconds, whether or not they hit the cache. Meanwhile, the request types enclosed in the blue box are those whose latencies are less than 500 milliseconds, whether or not they hit the cache. Now, you can readjust these boxes in many different ways, but the main idea is that some request types are more expensive than others. Now, what this means is 2 things. First, focusing on optimizing cache hits is insufficient, as it may cause unnecessary delays for cheap requests. And on top of this, naive load balancing can potentially impact overall latencies by causing expensive requests to miss and exacerbate delays. In the end, we want to avoid these cases, so we want to be able to prioritize hitting expensive requests and allow for missing cheap ones. And to do this, we need some sort of cache-aware, latency-driven scheduling to consider the utility of hitting the cache and ensure overall latency is not impacted by load balancing. And this is where our solution Kamino comes in. Kamino is a VM request scheduling framework which improves VM request latencies with cache-aware, latency-driven scheduling. Kamino considers cache state to improve cache locality, while also considering variable request latencies to minimize latency impact from load balancing. With these in mind, Kamino is able to reconcile cache reuse and load balancing, improving latencies while also improving memory usage. So let's talk about how we do it. To support our cache-aware, latency-driven scheduling, we build Kamino with the following architecture. First, we implement a multi-queue design to allow reordering of requests and enable the ability to induce cache affinity. Second, we add request classifiers, which pre-processes requests as they come in with useful information, such as its hash value used to look up cache state. Next, we add allocator agent selectors, which schedules requests across allocator agents in parallel, employing our novel lat cache algorithm, which we'll go in more detail out later. Lastly, we add a latency estimator to track request types and their historical hit and miss latencies. Now let's talk about the lat cache scheduling algorithm. The key idea of lat cache is to schedule requests where latency is minimized. Ideally, we would want to schedule a request where its cache result exists and load balance the request away only if the expected latency is minimized. To do this, lat cache schedules requests based on the following latency-driven model. The expected time for a request given an allocator agent equals the processing time for the request plus the queuing time for the agent plus the remaining time for the agent's current request. To actually compute this formula for when a new request comes in, we first derive the processing time by checking allocator agent caches and getting the estimated hit and miss times from the controller. We then derive the queuing time by checking the estimated latency of queued requests. And then finally, we derive the remaining time based on the estimated progress of the current request. To see this in practice, let's go through a simple example using two allocator agents. Let's say a new request comes in. The agent selector first consults the latency estimator to retrieve the estimated hit and miss times for the request. In this case, it finds it would take 20 milliseconds upon a cache hit and 50 milliseconds upon a cache miss. Now it computes the estimated latency for the first allocator agent. It derives the processing time by checking the agent's cache state. Since there's a cached result, the processing time would be the estimated hit time of 20 milliseconds. It then derives the queuing time by checking the agent's queue. In this case, it finds a single large request that would take 60 milliseconds. It then derives the remaining time by checking the estimated time left for the current request, which it finds to be around 20 milliseconds. It adds these values up to get a total estimated latency of 100 milliseconds. Now it does the same process but for the second allocator agent. It derives the processing time by checking the agent's cache state. Since there's no cached result, the processing time would be the estimated miss time of 50 milliseconds. It then derives the queuing time by checking the agent's queue, where it finds two fast requests that will hit the cache and take around 30 milliseconds. It then derives the remaining time by checking the estimated time left for the current request, which it finds to be 10 milliseconds. It adds these values up to get a total estimated latency of 90 milliseconds. In the end, despite the potential to hit the cache on the allocator agent 1, the overall latency matters more, so the agent selector decides to schedule the request to allocator agent 2. Now there's one more thing to consider, and that is hierarchical caches. While evaluation caches were previously shown to simply hold resulting sets for particular request types, in reality, evaluation caches have two levels. Top-level request caches hold resulting sets for particular request types, while lower-level rule caches hold intermediate sets for subsets of constraints. For example, let's say request type A comes in requiring a hard drive and GPU. The has HDDs rule is resolved to filter all the inventory to those with hard drives, and the has GPUs rule is resolved to filter the inventory to those with GPUs. The intersection is then taken to derive the final machine set for request type A. Now let's say request type B comes in requiring an SSD and GPU. It first checks the top-level caches to see if there's a cached result. It misses, so then it checks the lower-level rule caches to see if there are cached results for either of the constraints. In this case, it hits the has GPUs rule, but misses the has SSDs rule, so it only has to resolve the has SSDs rule to derive the final machine set for request type B. To consider this with lat cache, we create a lat cache variant which we call lat cache rule to track latencies at the rule level. With this variant, upon a top-level miss, the estimated processing time is set to the sum of expected rule latencies. For example, in the previous scenario, since request type B missed the top-level request cache, its processing time is set to the hit time of the has GPUs rule plus the miss time of the has SSDs rule. So how well does Kamino perform? To evaluate Kamino and lat cache, we simulate system performance with 6 traces from high-traffic nodes. We compare the following approaches: Protean, the original system using a shared queue for load balancing; hash plus work stealing, the approach previously mentioned in our motivation; lat cache, Kamino's latency-driven cache-aware scheduling; and lat cache rule, the lat cache variant with more precise rule latencies. Lastly, for each approach, we measure the average and tail latency, as well as memory usage and cache hit rates. Let's first take a look at the improvements for average latency. On the x-axis, we have the different systems, and on the y-axis, we plot the latency improvements compared to the baseline Protean system. The higher, the better. We see average latency improvements of 34% with lat cache and 42% for lat cache rule. For 90th percentile tail latencies, we see improvements of 50% for lat cache and 55% for lat cache rule. Overall, lat cache's latency awareness is able to improve latencies by avoiding expensive misses and unnecessary delays. Lastly, not shown, lag cache improves cache hit rates by 13% and reduces memory usage by 15%, demonstrating how its cache awareness maximizes reuse while minimizing duplication. Next, we want to see, how does Kamino's lag cache perform in practice? To do this, we deployed Kamino with lag cache across 5 Azure production zones. We compared the performance before and after deployment, measuring average and tail latencies, cache hit rates, and memory usage. Here we plot the average latencies before and after deploying Kamino on top of Protean. On the x-axis, we have the different zones, and on the y-axis, we have the average latency normalized to the largest latency experienced in that zone. The lower, the better. After deployment, we see that the average latencies improved by 21% and tail latencies improved by 12%. One thing to note is that not only does this show how well Kamino improves latencies in practice, but also demonstrates how local level optimization translates to zone-wide performance across many allocator nodes. Lastly, we plot the aggregated hit rates across the zones over a 2-month period. On the x-axis, we have the date in days, and on the y-axis, we have the aggregated hit rate. The higher, the better. After Kamino's deployment, we see cache misses reduced by 33%, improving cache hits by 8%. Next, we see memory usage reduced by 17% across nodes, again demonstrating Kamino's cache awareness and ability to minimize cache duplication. To conclude, we presented Kamino, a VM request scheduling framework that improves VM request latencies with cache-aware latency-driven request scheduling. Through cache-aware latency estimation, Kamino is able to adapt to request latency variability and prioritize cache locality for expensive requests. With latency-driven scheduling, Kamino is able to reroute requests only when beneficial, effectively reconciling cache reuse with load balancing. This results in overall latency performance and memory usage, translating to more efficient scaling to available hardware. And with that, I'll conclude my talk. Thank you, and I'm open to take any questions.